Hello everyone, I'm Said and I'm pleased to present on the topic of semiconductor laser operation. This presentation will provide a comprehensive understanding of principles, structures and application of these lasers. These are the outlines of my presentation, including introduction, historical perspective, basic structures, working principles, energy band diagram, types of semiconductor lasers, advantages and challenges. Semiconductor lasers are among the most critical innovations in photonics. They are compact, efficient, and they are able to generate coherent light, so they are essential in modern technology nowadays. And their function based on electronic transitions between conduction and valence bands within semiconductor materials. The common materials that we are using for semiconductor lasers are mentioned here, but the most commonly used materials are gallium arsenide and gallium nitride. I can say here that by using gallium arsenide we can release the photon or light, but whereas by using gallium nitride we're gonna have heat. So it's very important what kinds of material we are using. As a result, we're gonna have different kinds of semiconductors. But in this presentation my focus is on a semiconductor lasers and gallium arsenide material. As you probably know that laser diodes is a kind of semiconductor lasers, and these lasers have different applications in telecommunication, electronic devices, medical area, in industry, for laser cutting, material processing, and in defense and security, also in for example LiDAR systems, and in scientific researchers in different kind of devices like Raman and spectroscopy and optical trapping. Before talking about the structure and basis of the semiconductor lasers, we're gonna have the historical perspective, the early work, the early concepts and invention in this field was in 1958, and after that different researchers work in this field, and actually the usage of semiconductor lasers was very expanded, and recent innovations in semiconductors is in advances in quantum dots and photonic crystals that have enhanced their performance and their usage. About the structure of the semiconductor lasers, I can say there are some key components, including active region, which is between two N cladding layer and P cladding layer, and cladding layers that surround the active region. The active region is a region that actually it's the heart of the laser, and where electron hole recombination occur. We're gonna have PN junction, which provides the medium for charge carrier injection, electrodes and waveguides and reflective mirrors. Semiconductor laser work based on simulated emission. Usually electrons are injected into the conduction band and the holes into the valence band. When electrons drop to the valence band, they emit photons. When the recombination occurs, we're gonna have the emission of photons or light. And Also, when a semiconductor is doped, part of it becomes p-type, and the other part is n-type, forming forming a p-n junction. And this in this area also is named depletion region. That in this region the recombination of electrons and holes occur. There, as I mentioned, that there are combination of electrons and holes. As a result of this process, we're gonna have the emission of photons and light. The working principle of a semiconductor laser can be best understood through its energy level diagram. This is the energy level diagram. This is the conduction band, the higher energy level, and this is the valence band, the lower energy level, and this is the Fermi level. As you can see that the Fermi level indicates the energy states filled with electrons at thermal equilibrium. The Fermi level is the same in both regions, as you can see in this video. So actually the Fermi level of the p-type moves down, and the n-type moves up, as you can see. And then electrons are pushed from the n-type region, and holes pushed from the p-type region into the depletion region. And in this region we're gonna have the recombination, and so as a result of recombination of electrons and holes, we're gonna have the emission of light or photons. So as I mentioned that we're gonna have different kinds of semiconductor lasers. You can see, and they have some advantages, including compact size, high efficiency, coherent light, and their fast modulation, also durability. They have long operational lifespan. And these kinds of lasers have some challenges, including some of them are very expensive. Also, temperature sensitivity is very important because it can affect on their performance. And the material challenges, it's very big challenges, because they're using semiconductor materials, and other challenges that you can see. And these are the references that I use in figures and photos, pictures, and the information I use. Thank you for your attention.